Something that comes through in the normal model are z-scores. It's a standardization of our normal model, the idea being that our bell-shaped curve always looks the same. So we always have a bell-shaped curve, and then we always have this idea of what's expected, having a high probability of occurring, and then how those probabilities decrease as we're above or below. So with this, z-scores make a way for us to compare bell-shaped curves that are different from each other. If it's just the number line that's different, we can still compare them in terms of what's expected and what's less likely due to how many standard deviations away it is. So it helps us compare unlike events. Even if two events are quite different, like what we're going to do is compare Portland rainfall to Chicago wind speed. And these behave very differently. They have different units, they have very different expected values, different standard deviations. What we want to do is be able to compare the likelihood of events. So we can use the standard deviation as a ruler. Meaning what we can do is create this kind of standardized number line such that what if we made 0 the idea of landing on the mean? So then if we had 40 inches of rainfall, we would say that's average for Portland. Let's equate that to the mean. Then what we could do is use a number 1 to represent one standard deviation above. So in terms of rainfall, that would equate to 48 inches of rain. If we're working with Chicago wind speed with an average of 10, standard deviation of 2, it would be the equivalent of 12 miles per hour. But what we end up with is this number line where we can equate different values, but this brings through kind of equal likelihood of seeing those two values. And then we could look at 2, and we could keep on this number line. But this would be the idea of having one standard deviation above the mean. And then 2 would be 2 standard deviations above the mean. And then we could have negative numbers, where -1 would mean 1 standard deviation below the mean. So it'd be below average, below what we expected. So we can use these numbers as a way to compare these unlike events. So let's see how this works out with Portland and Chicago. So with Portland, they tell us we have an average rainfall of 40 and standard deviation of 8. And then Chicago has wind speed of an average of 10 miles per hour, standard deviation of 2. And what we want to do is, where we see these two events, Portland had a rainfall of 24 inches, Chicago had a wind speed of 13 miles per hour. Which of these two events were more extraordinary? Which just means which was furthest from expected, or rather furthest from the mean. So what we can do is, we know where the mean's landing exactly. What we need to do is put in terms of how many standard deviations away. So to do this, we use this formula. This gives us the measurement in terms of standard deviations. So like with Portland rainfall, we have this average of 40, standard deviation of 8, and we saw this value of 24, and we want to compare that to our mean and standard deviation. So what we're doing with this z-score is we're looking at our distance from the mean first. So we take 24 minus 40. So if we carry out that subtraction, that'll tell us how far from the mean we are. But that distance that they're giving would still be in rainfall. It would still be in inches of rainfall for Portland. So we still wouldn't be able to compare that to Chicago, where they have a mean of 10, standard deviation of 2, and they saw this value of 13. So that for their z-score, in their numerator, they're taking 13 minus 10, which again gives us a distance away from the mean, but it's still in miles per hour. It equates with being 3 miles per hour away from the mean, and this other one, we have this distance in rainfall. So this is where we need to divide by our standard deviation. So we have this distance, but we're going to cut up that distance in terms of these standard deviations of 8. So now we have this distance, and it's giving us our value in terms of standard deviations. And here, where we have this distance, cut up that distance based on having standard deviations of 2, and what we'll get are these two numbers that we can compare to each other. But for the calculation, the numerator is looking at the distance between the value and the mean. And that denominator is creating units in standard deviations. So, with Portland, what this is telling us is that 24 inches of rainfall in Portland is 2 standard deviations below average. And for Chicago wind speed, let's see, that's 13 miles per hour wind speed in Chicago. Is 1.5 standard deviations above average, since it's positive. So what we can do now is compare these two values. So again, with that number line that we were talking about, where basically zeros are expected, then we could go like 3 standard deviations above, 3 standard deviations below. Then what we can see is where Portland's landing. Portland's landing down here at 2. That was 2 standard deviations below, and Chicago is landing up here 1.5 standard deviations above. Now, in terms of which one was more extraordinary, which one's furthest from the mean, well, if our mean is at 0, then Chicago is just 1.5 above, and Portland is 2 below. In terms of distance, Portland is further away. So Portland was more extraordinary. Getting a rainfall of 24 inches was more extreme than a wind speed of 13 miles per hour in Chicago. So we can compare these two things with completely different units using z-scores. Now, with this number line that we're making, our mean is here at 0, and as you can imagine, with gathering data, if we were gathering data from Portland or from Chicago, being 1 standard deviation above, 1 standard deviation below, it's likely to land between those two values there. And then, as we move out further and further, it becomes less and less likely. And what that's describing exactly is our bell-shaped curve. What we would do is we'd have a bell-shaped curve, our peak at 0, because that's where our mean is, and then it would decrease out like that. So this number line completely matches up with how we talked about the normal model before, being 1 standard deviation above, 2 standard deviations above, 1 standard deviation below, 2 standard deviations below, 3 standard deviations below. It's just this special number line that's based on z-scores. So our number line here is for z, where z is -2, or z is 1.5, z is 0. And with that, we have a special name for this. This is called the standard normal curve. But it's basically a curve for z-scores. And this curve for z-scores that's coming out always has a mean of 0, and then our standard deviations that we're moving by are 1. So it's this curve that's normally distributed, mean of 0, standard deviation of 1, which when we started up GeoGebra, this is the curve they start with. And it's a standard normal curve of z-scores. A lot of textbooks and resources really rely on this curve. As we could see, we can always edit our mean and standard deviation, so it's not as necessary anymore, but this is a curve you could use and always go to no matter what data value and mean and standard deviation you have. With this formula, you can always create a z-score from the scenario you're looking at. So this information's gone over in this page here. Standardizing into z-scores doesn't change the shape. We're still bell-shaped, so we still have a bell-shaped curve. The center becomes 0, so that's our mean. And the spread, our standard deviation, is 1. So just be careful of wording here. If they just say it's a normal curve, then that's where your mean and standard deviation could be anything. But if they use the word standard normal, that automatically makes it so that you're working with mean of 0, standard deviation of 1. So just by adding that standard word, it sets your mean and standard deviation. And also, even though GeoGebra is still going to show you x, this is technically for values of z. So if you're ever looking for like probability z is something, this is the curve you want to use in GeoGebra. So normal distribution model has a mean and standard deviation. Standard normal model has our mean of 0, standard deviation 1. Here's our formula. If you use sample values, it's the same formula, just with mean and standard deviation in terms of sample data. Either way, it's fine. All right, so standard normal, this is what we drew on that other page, but it's always going to have this number line. So say we wanted to find these different probabilities, like a probability that z is less than or equal to 0.5. And really, I wouldn't write this as an exam question, but I technically could give you this without any other information, and you should be able to find it. The key part being that if we have z, as soon as I see z as my variable, I know I'm using a normal curve with 0 and 1 for my mean and standard deviation. Same thing with this next one. Since that's z right there, then I know I have normal curve, 0, 1. But if this had just said p of x is less than or equal to 1.5, then I need more information. I either need to be told it's a standard normal curve to use that mean of 0, standard deviation 1, or I need more wording saying specifically what is my mean and standard deviation so I can use it. But since I have z, then we'll just go to GeoGebra, and we'll have our mean of 0, standard deviation of 1, and we're looking for something that's less than or equal to 1.5. So this is going to go to our left-hand side. So left-hand side and a positive 1.5. And that's going to be a 0.9332. So this right here with mean of 0, standard deviation 1, there's our normal curve, standard normal curve. And then from there, even though GeoGebra is still going to show x there, it is technically z given that mean and standard deviation. So 0.9332. If we wanted to look between negative 0.3 and positive 0.5, what we can do is plug in negative 0.3, positive 0.5, and we have our same mean of 0, standard deviation 1, and that's a 0.3094. All right, so that's how we can find probabilities. You can also do the reverse of given percentiles with z-scores and finding cutoff values. That's how we work with those z-scores. Let's do an example where we're again comparing two different types of exams. We have a student who took a placement test for French and math. And for French, they got a score of 82. In math, they got a score of 86. And that gives us information about how other students did, their average and their standard deviation. So on average for the French exam, they expected a score of 72, and standard deviation 8. And for the math exam, there's an expected value of 68 and standard deviation of 12. So in terms of figuring out which exam she did better on, we can't just compare the 82 to the 86. Even though that's showing the math score is better, what we need to take into account is what do we expect and how does it spread for the students? So for the French exam, we expect them to get a 72, and on average that deviates by 8. So what that does is it gives us an idea of how the other students are doing, and when we see this 82, we want to compare it to that. And same thing with the 86, they expect a lower score of 68, but there's a lot of spread to it with the standard deviation of 12. So we don't really know if that 86 is very far away or close by to what's expected. So what we want to do here is compare their z-scores. Since we can't just interpret the difference just looking at those three numbers, we need to combine them into a single value. So z-score, take 82 minus 72 over 8, which will be a 1.25. And for the math score, taking the 86 minus 68 over 12, which is a 1.5. So in terms of which was more extreme, in this case, it's which did she do better on? So for this, we do want a z-score that's positive. If she had a z-score that was negative here, that would be the idea of performing below average, which isn't good on taking tests. So we want above average. Both of these are positive, so we're good there. And then we just want which one is further above average. And comparing those two values, I mean, we could do our number line again. And it's that French was at 1.25, math was at 1.5, and math was further above. So she did do better on the math exam, but we couldn't just compare the 82 and 86, even though that kind of confirmed our suspicions that math was better, but we had to take into account mean standard deviation as well. So math score was better. So this is how we can use the standard normal curve and z-scores to compare values.